but the US Department of Transportation defines it as any material or mixture that has a pressure of more than 40.6 psi absolute at 20 degrees Celsius. They like mixing units for some reason. Normally, compressed gases will be supplied on the smaller scale in gas cylinders, just like those ones on the left. They're usually very heavily built. Typically, there'll be a carbon steel cylinder. The most common ones for normal industrial applications are usually around 2200 psi, depending on what the gas is. There are also higher pressure cylinders that are available, but they're usually more of a specialized item. But you might well encounter the higher pressure ones as well. One of the important things to note with any gas cylinder is they all have their own unique fitting on them that's intended for a particular gas or a particular family of gases. And there's an organization called the Compressed Gas Association, or CGA, which defines all these different standard fittings. So there's a standard for oxygen. There's a different standard for inert gases like nitrogen and helium. And this is done very deliberately to make sure that you can't accidentally connect hardware that was intended for one gas to a cylinder that it was not designed for or isn't compatible with. This is a really important safety feature, and so it's usually frowned on to try to do things like using adapters to cheat that. They're there for a reason, so you should stick to it. When it comes to storing gas cylinders, you saw in some of the earlier videos what can happen if they topple and knock the valve off the top. While those cylinders are pretty heavily built, the weak point is definitely the valve on it. And so they will usually be supplied with metal caps that thread onto the top. Whenever it's not being used, the best practice is to keep it capped. Definitely whenever it's being transported, any regulators or plumbing need to be removed. The cap needs to be put on, and then you can transport it. When you're storing them, they should be chained upright so that they can't topple. You want to make sure that they don't get overheated. So typically they'll say don't heat them above 50 Celsius. They usually also don't like to get very cold. They are carbon steel, and carbon steel does tend to get brittle at low temperatures. So if you ever were thinking of chilling one below minus 40 Celsius for some reason, don't. The other thing that's really important is that any moisture getting into the valve can very easily interfere with its ability to seal properly, or it can actually plug the valve. And so if it's cold and wet, you want to make sure that the valves always stay dry. So when you're transporting them, as I say, always use a protective cap. Never ever transport it with a pressure regulator attached, because if it did topple, it's very, very easy to catch the regulator and that can shear off. These things are heavy. Any significant sized gas cylinder is more than one person can easily move by themselves. So it's always a good idea to make sure that you're using a gas cylinder cart or using a couple people. It was mentioned earlier on that anything more than about 35 pounds, you want to have two people carrying it, and that's true with gas cylinders as well. So don't be a hero when trying to haul around gas cylinders. So when you're using them, that image shows, typically what's on the head of a gas cylinder. There will be a manual valve. There will usually be a rupture disc or other relief mechanism. Those are there for a reason. Don't try to get around that. Just like what those heroes with their liquid oxygen cylinder did, you don't want to mess around with any overpressure protection. Now the threads on the connections on gas cylinders are not designed to be lubricated or used with Teflon tape. So Teflon tape is something that Often you'll use, if you've got pipe threads, they're not for these types of fittings. So you just connect them dry. When you've connected up a cylinder, you want to open the valve very, very slowly. Usually, if there's something that you forgot to tighten properly, any leaks, any problems, it'll be obvious pretty quickly. So you don't want to just crank a cylinder valve open. You want to give it a chance to very gently build up the pressure. And then you can close it again if you hear any leaks or if anything goes wrong. Whenever you've got a cylinder connected to something, if you want to remove it again, make sure that the lines have been depressurized and that the valve on the cylinder has been closed before you start undoing any connections. Without that, then you can very easily find a fitting firing off or a hose whipping around. So it's important to make sure that there's no trapped pressure before you start disconnecting something. Another thing that the gas suppliers will always remind you of is never to discharge a cylinder below about 25 psi. You want to make sure that you can't get contamination back into the cylinder. So keeping a bit of positive pressure in there will help to prevent that. Similarly, if you've got multiple cylinders that are ganged together on a common manifold, you don't want to allow any cylinders at lower pressure on that manifold, because they will tend to backflow from the higher pressure cylinders. And again, that can lead to contamination. So on top of all of this stuff, there are also going to be specific hazards related to whatever gas is in the cylinder, whether it's oxygen, hydrogen, what have you. So you need to be aware of the specific hazards related to those fluids as well. Now, system design. Scott gave a really good overview of that. I'm going to touch on a couple general guidelines for specific components. One of the things that I should stress is that this is not going to be primarily a design course. Again, we can't cover everything, but I want to try to give you all a sense of the general types of hazards that you should be aware of when you're choosing components. Yeah, question at the back. Okay, so the question was, if you've got a gas cylinder and the valve on it starts getting frosted up because either of expansion through the valve or because it's cold out, what do? Do you need to wipe it off? The real concern is when you're making a connection. So if you've got a disconnected cylinder and you've got moisture inside it, that's where you're going to have a problem. Any condensation or frost on the outside isn't going to be a big deal. Okay, so when you're looking for components for a system, you're probably going to end up doing one of two things. You might source components from a supplier, or you might find yourselves designing your own. So when you're sourcing components, you need to learn how to size them properly and how to specify to a supplier exactly what you need in that component. When you're designing your own components, because maybe there isn't something off the shelf that's going to work for you, you need to understand how to design those things safely for your application. So we're going to try to give you some of just the basics that you need and point you in the direction of some material that will hopefully help you to do that as well. So the first thing I want to look at here is safety factors. We've talked a lot about that earlier on, but in general, safety factors are usually quoted based on the ratio of the ultimate strength of the material to the allowable stress. They are going to be normally based on the maximum pressure that the vessel or system will ever be expected to experience. So normally your operating pressure will be somewhat below that. But the safety factor is going to be based on, the relief valve pressure or whatever the limiting factor is on the pressure in that system. These need to be carefully considered to deal with both your regular operating conditions as well as any off-nominal events. When you are designing to a particular factor of safety, you've got to think about the context this is going to be used. So normal practice is if you've got a system that people are going to be physically close to while it's pressurized, safety factor cannot be below 4. If it's a system that's going to be used in an environment where it's going to be exposed to considerable shock and mechanical strain while people are close to it, then that goes up to 6. If it's going to be in a hazardous situation or contains hazardous material, then your safety factor goes up to 8. So these are the normal industrial practices for these systems. On top of those best practices, ultimately why you're using a safety factor is to account for any uncertainties that exist. So in any design, there will be uncertainties. Uncertainties in your own calculations, uncertainties in your analysis, uncertainties in the actual operating conditions it's going to experience, or in the material properties, or in the manufacturing processes. So generally, the more the uncertainty is, the higher your safety factor needs to be. In aerospace applications, obviously weight is really important. So if you go back a couple hundred years to when engineering was primarily civil engineering, the way they tended to address these uncertainties was to use big safety factors. With aerospace, it's harder to do that. And so in order to drive your safety factors down, it means that you've got to do a lot more careful design work, more careful analysis, and potentially more careful testing in order to make sure that your lower safety factor is still going to be safe enough for the application that this was designed for. Now, there are 2 standards in particular that are really good references for any high pressure systems. And for systems that are going to be used as part of either ground support equipment or test equipment, generally everything should be designed in accordance with these 2 standards. So there's ASME B31.3, which is their standard for designing piping systems, fittings, and components. And Scott had mentioned that earlier on. It gives you stress allowables for different materials and gives you guidance in how to size things, as well as what kinds of processes you can use to join components and what sort of testing needs to be done. If you're getting into developing your own pressure vessels, those will typically fall under the ASME boiler and pressure vessel code. So this is a very comprehensive code for the design of industrial pressure vessels. And they've got a whole bunch of different sections that you'll probably want to consult related to materials and types of non-destructive testing you can do, construction approaches, welding and brazing qualifications, and a whole section on composite pressure vessels as well, which is an entire subject in its own right. Now, these are the standards for normal industrial vessels. In a lot of aerospace applications, you'll hear people refer to non-code vessels. So what that means is any pressure vessel that isn't designed to the ASME boiler and pressure vessel code. And for flight weight systems, you will very frequently need to use lower safety factors and design non-code vessels. And that's okay, but you need to remember that, if the safety factor is below 4, no one can approach it while it's pressurized, or no one should approach it. And if you want to try to preserve safety with a lower safety factor, you need to do the analysis and the testing to substantiate that your design is actually going to be safe. So material compatibility. Whenever you are either sourcing components or designing your own, you're going to need to pay very careful attention to making sure the materials are compatible. And we looked at a couple of cases earlier on of what can happen when the materials aren't. This is going to include not only the really obvious things like tank materials, tubing, piping, valve components, but it also includes things like seals and gaskets and brazing materials or welding materials, lubricants as well. So all of these things are really important to consider, and not just what the basic material that a part is made of is. And again, ASME B31.3 gets into some of these considerations. Also, the ASTM Manual 36 that the NASA Lock Systems training was based on is going to cover a lot of those particular requirements as they relate to oxygen systems. But just in general, any material that you're using has to be compatible under all of the conditions that they're going to be exposed to, and not just the nominal. So you've got to be really creative in thinking about what those weird, unforeseen cases could be that could end up sizing things. Your materials are going to have to resist oxidation, potentially, corrosion, maybe abrasion, maybe shock, maybe temperature. So all of these are factors that relate to the environment that they're going to be used in. And of course, it's got to make sure that your materials don't form any sort of explosive mixture with the fluids that are being used. And particularly with oxidizers, this is really important. So a petroleum-based lubricant in a liquid oxygen system is an explosion waiting to happen. So it's really important to get down to that level of detail. As another extra special note, you never ever want to use a carbon steel in any low temperature or cryogenic applications, because carbon steels in particular get very brittle at those temperatures. You also need to make sure that if you're designing an oxidizer system, you don't just need to evaluate the materials in that system for their compatibility. You also have to look at anything upstream of it. So your pressurization system mustn't introduce any contaminants that could make their way down into the oxidizer system. Same thing with any purges or fill systems. Another guideline that's usually made is fluorinated hydrocarbons such as Kel-F are not considered safe to use in contact with aluminum in a gaseous oxygen environment. That's sort of a more specific one, but it goes into the kinds of funny material interactions that you can run into. So once you've kind of sourced your components, yes, question. Why not titanium? Because titanium will burn. Yeah, most materials in an oxidizer system are flammable to some degree. So even something like stainless steel, which is considered to be compatible with oxygen, will burn under certain conditions. So it's never going to be a question of having zero possibility of something igniting. Rather, it's going to be ensuring that that the chances of that happening are reasonably low under the conditions that it's going to be exposed to. And I think that's another really important aspect to system design, because safety is context dependent. A material choice, for example, that might be suitable in one application won't necessarily be suitable in another one. So oxygen at lower pressures is very different than oxygen at higher pressures. And so you've got to make sure that you account for the specifics for all of these things. But titanium is usually considered to be a major fire hazard for oxygen service in general. Also, it's really expensive. So if you're thinking about using titanium, then you're going to need to make sure that your budget can withstand that. So when you're laying out your system, this is actually a piece of system design that's really, really important. It's not just about looking at all the components you need and putting them in place. You need to think about physically where they're going, how plumbing is going to be routed, how things are going to be mounted. And so this is part of what happens in taking your P&ID and turning it into a real functioning system. And whenever you're doing this, one of the things that's important to keep in mind is to keep your system as neat as possible and as accessible as possible. It should be visually obvious what a given line is connected to, so that you can immediately tell if something's leaking. If you're seeing or hearing a hiss, you should know exactly what this is coming from. And if you've got sort of a tangled spaghetti of plumbing, it's much harder to do that, and it's much harder to trace anything. You also need to make sure that you've got enough space that you can physically get at any connections that you need to have access to. It's really, really easy to design a system so that it looks like you've got plenty of space, but then you discover that you can't actually get a wrench onto a component that you need to tighten. So it's important to think about these usability aspects as well. You want to generally try to design things so that no single malfunction or misoperation of any component could lead to a major hazard. So you want to try to contain any hazards, and you should always be really creative and imaginative in thinking of weird ways that things can fail. Hopefully some of the spot the hazards cases that we looked at earlier on have given you a bit of a sense that unexpected and puzzling things really can happen. And so you need to always try to stay ahead of the game by thinking creatively about, what happens if this thing fails at a very specific point, Generally, your systems should allow lots of clearance around components if possible. And on top of that, as we looked at earlier on, things will leak. And so it's not necessarily a question of if they'll leak, but when. And so you want to anticipate that and think about, if a leak occurs, where is that leaking thing going to go? And if two things leak at the same time, what's going to happen? Are you going to have those leaked chemicals mixing and creating an even greater hazard? So trying to design around that. So for example, you don't have fuel and oxidizer leaking into the same place is really important. Related to that, you need to also think about where your vent valves or relief valves or rupture discs are going to go when they either leak or open and vent normally. Scott had mentioned that it's pretty normal to dump smaller quantities of liquid oxygen onto concrete. Never ever do that on asphalt. Concrete is fairly safe. Asphalt will form an explosive mixture with liquid oxygen. So these are the kinds of things that you need to try to think about. And so if you've got something like that, you don't want to route an oxygen vent or an oxygen relief line to those areas. And of course, obviously, fuel and oxidizers don't go well together. So you want to try to make sure that they're venting or relieving to physically separate places so that there's no possibility of simultaneous venting causing cross-contamination or mixing. Now, on top of these things, shock is an important consideration. So there was some discussion earlier on about water hammer. And so if you close a valve very suddenly and you've got a long stretch of plumbing upstream of it, then the momentum of that fluid suddenly coming to rest can create a pressure wave that could propagate back up through the plumbing, and there can be a significant temperature rise across that pressure wave. And so there have been cases where that phenomenon has created enough energy to cause things to ignite. And so designing your system to try to minimize the chances of that happening is going to be really important. These things become particularly problematic if you've got very high fluid velocities. So a very common practice is to try to limit those flow velocities in something like a liquid oxygen system. Another thing that's going to be an important consideration is thermal expansion and contraction. Particularly if you're dealing with a cryogen, as things get cold, they're going to shrink. And you've got to make sure that as they do that, it's not going to create undue stress on your system, because if you put stress on fittings, they can start to develop leaks. So making sure that there's enough flexibility built into your system that it can take any of the thermals it's going to experience is going to be really important as well. So doing some basic calculations to look at just how much thermal contraction or potentially expansion something is going to encounter is going to be really important. The other thing that is really important, as Scott had mentioned earlier on, is that fluids expand as they warm up and cryogens will boil off. So any trapped sections of plumbing need to be vented to prevent them from overpressurizing. So as a couple general comments, when you're selecting components, always make sure to assess the component you're looking at for your specific application. It's pretty common that people will, use an industrial off-the-shelf part in, say, a liquid oxygen system or in some situation that it wasn't explicitly designed for. You need to be really careful if you're doing that. It's not impossible to do that with some components, but it does mean that you're going to have to very carefully evaluate. So if you've got a part that was designed for, say, a valve designed for 1,000 psi at room temperature, don't assume it's going to work just as well at lower temperatures or at elevated temperatures. You've got to look at all of these things for your specific application. You never want to operate a component outside of the conditions that it was designed for unless you've already done the testing to make sure that it can operate safely in the way that you're planning on using it. And you need to make sure that you confirm the compatibility of any wetted parts, so any parts inside a component that are going to come in contact with the process fluid to make sure that they're compatible with the fluids they're going to be exposed to. You're also going to need to make sure that any components are sized properly for the flows that they're going to have to accommodate. So it's not enough to just put a pressure relief valve on a tank. The pressure relief valve has to be large enough to be able to handle the full flow rate that's causing the dangerous overpressure situation that you're wanting to avoid. Obviously, you need to make sure that any components have a suitable pressure rating for your application. And again, that applies for the complete range of conditions that it's going to be operating under. When you're finding sources for valves, typically those are going to be sized based on a CV coefficient. That's a standard correlation, and you can look at how you convert CV to flow rate for different fluids. It's a pretty standard thing. You'll often also see flow curves provided with particular components that will rate the flow rate and pressure drop with some standard fluid like air or water. And so using those flow curves, you can size them for your own particular application. Plumbing itself is usually going to be sized based on the allowable pressure drop in the line and the allowable flow velocity of your fluid. So generally, when it comes to something like an oxidizer, you want to limit those velocities. There are various numbers that are floated around as standards for that, but typically oxidizer systems, you don't want to be running at more than about 60 feet per second. And ideally, it's a good idea to keep them even well below that. Any velocity to your flow is potential kinetic energy that could be imparted to any debris in the system. So by limiting that velocity, you limit the potential of something catching on fire due to an impact of debris inside the system. So specific types of components you're probably going to want to use. Pipe and tube. People sometimes use these terms interchangeably, but they actually do have very specific definitions. So a pipe is a thick-walled duct that can be threaded. So typically, pipe will have a tapered thread on the end that can be threaded into a matching tapered fitting. Pipe is usually sized based on a nominal size and a schedule number. So the nominal size is sort of an approximate internal diameter, and the schedule number tells you what the wall thickness is going to be. The challenge with pipe is that pipe is heavy. And so pipe is usually less common in flight weight systems than tube. The fittings on pipe are usually NPT fittings. That's a North American standard. There are other standards in use elsewhere, but generally these are tapered fittings. So a normal screw thread is not a very good way of making something leak tight because there's going to be this spiral leakage path along the threads. NPT fittings get around that by using a tapered thread so that as you tighten up the fitting, it jams the threads against each other. And so when you wrap those fittings with a sealant like a Teflon tape, it'll give you a very good seal at the same time as it mechanically holds the parts together. So that's typically what's done with pipe fittings, but as I say, they're quite heavy. Tube, on the other hand, is thin-walled, so it's not thick enough to put a thread in it. It's just designed to contain internal pressure. And so to join tube, you need to do something else than just threading it. And the most common ways of joining tube will be either things like welding or brazing, or by using tube fittings. And there are various types of tube fittings that you can use that we're going to get to in a moment. One note on tube is that usually it's available in either seamless or welded varieties. Preferably, you want to be looking at using the seamless type, particularly if you're going to be using it with any tube fittings, where sometimes having a weld bead can compromise the ability of it to seal properly. And again, you know, anytime you've got something that's welded, that's something that can fail. So seamless tubing will typically have a higher pressure rating for a given tube than the welded variety. Then there's a third one, hose. So sometimes you're going to want to have something that's more flexible than a rigid tube or pipe. And so that's where hose comes in. But hose is usually considered to be a poor second choice to tubing. That's mostly because it's a lot more failure prone and it's more prone to whipping around if anything comes disconnected or if the hose bursts. Tubing usually will consist of some sort of flexible internal liner and will often also have some sort of external reinforcement to allow it to take higher pressure. So for aerospace applications, one of the most common types of hose you're going to see will use a Teflon liner and a metal mesh overbraid to give it strength. That's a pretty common type of hose to use. It's generally not suitable for use at cryogenic temperatures because the Teflon can get harder and can crack. If you're working under extreme temperatures, either low or high, the most common way of doing that with a hose is going to be using bellows. And so bellows, for any who aren't familiar with it, is basically a corrugated metal duct. It looks a lot like a vacuum cleaner hose, and the corrugations give it a certain amount of flexibility. Often it'll also get a metal mesh overbraid to give it additional strength. The downside with bellows is that bellows has very high pressure drop, many, many times the pressure drop of an equivalent length of tubing. So if you're wanting to use bellows, typically you want to limit the length of bellows that you need. The other thing that's challenging with bellows is those corrugations inside are really good at trapping debris. So cleaning becomes really, really important if you've got something like bellows. Now, when you're making connections, one of the most common things you are going to see is these NPT tapered pipe threads. They jam together as they are done up, and usually a sealant is going to be used to make sure that you don't get any leakage past the threads. It's always really important to look at the specific sealant you're planning on using to make sure that it's compatible with your fluid choice. So Teflon tape is the most common thing, and a lot of applications will use it even under cryogenic conditions. So it's usually a pretty good choice. There are other pipe joint compounds that are going to be more restrictive in the sorts of applications you can use them. So you need to pay attention to that if you're using NPT fittings. But NPT fittings are not generally the ideal choice for most rocket applications. Partly that's because it can be difficult to get them to seal properly, and it can be really difficult to get them to align properly as well if you need to clock something to a specific orientation. They can also tend to be leak prone if they're rapidly being chilled down to cryogenic temperatures and warm back up again. So these are just some of the pitfalls that you can run into with pipe. One of the most common fittings to use with tubing are what are commonly referred to as AN fittings. So these are 37-degree flared fittings. The left side there, you can see what the end of one of those fittings look like. It's got a tapered conical nose and then a thread. On the tube side, you flare the end of the tube to match that 37-degree cone, and then there will be a sleeve and a nut that slide over the tube. And when they thread it on to the thread on the mating fitting, it pulls up the flared end of the tube against the nose of the fitting, and that's what makes the seal. So these have been common for aerospace applications since pretty much World War II. They're a relatively reliable type of fitting to use. They're available in a whole different range of materials. Aluminum and stainless steel tend to be the most common. It's important to note that with these types of fittings, unlike pipe fittings, you do not use Teflon tape or any other sealant on the threads because you don't need to seal the threads. The threads are only providing the mechanical connection that draws the parts together. It's also important to note that there is an industrial grade of this type of 37-degree fitting that's commonly called a JIC fitting. Those are most commonly available in regular carbon steel, which you don't want to use for any oxygen system. They are technically interchangeable with AN fittings in that you can physically connect them up, but they're not made to as tight tolerances. So your mileage may vary if you're using JIC type fittings in place of AN. Another type of fitting that you're probably going to see a lot of is these compression type fittings. And there are lots of different designs of them, but one of the most common that you'll probably encounter is the swage lock fitting. And that's an example of a swage lock fitting on the left. Basically, these fittings include one or two ferrules that usually come pre-installed in the fitting. So you insert the tube into the fitting through the ferrules, and as you do up the nut, it drives the ferrules down and inwards so that they bite into and swage the tube. And so the ferrules become a permanent part of the tube, and they both give you a mechanical connection and a seal to the body of the fitting. So these are nice because unlike with AN fittings, you don't need flaring tools to make those flares. All you need is a wrench to do up the fitting. The downside with these types of fittings is that with an AN fitting, if something isn't torqued properly, the fitting might leak. But with one of these, if the fitting isn't torqued properly, you can actually fire the tube out of the fitting. And I've seen that happen a couple times. So it's really important to make sure that you do them up properly. And again, that you increase the pressure very, very slowly to make sure that you're getting a proper seal. Now, I showed the swage lock version here. There are lots of other variants that are, in some cases, less expensive than the swage lock fittings. Again, you've got lots of choices. Your mileage may vary. Another type of component that you're going to be using a lot of will be seals, and probably the most common type of seal you're going to encounter will be O-rings. O-rings can be used for both static seals as well as dynamic seals if you've got anything that is going to call for a dynamic seal. But it's really, really important to never use an O-ring outside of its approved temperature range. Everybody knows what happened when they did that on the Space Shuttle Challenger. There are a whole range of different materials that are available for O-rings. Most of them are going to be elastomers, and they'll come with their own, materials compatibility and their own temperature ratings. Important to note that elastomeric O-rings generally are not compatible with liquid oxygen. For that, you typically have to go with something like Teflon. Teflon is a nice material because it's very inert in most cases, but the downside of a Teflon O-ring is it's not a rubber, it's a plastic. So it can be very challenging to get a Teflon O-ring onto the end of a fitting. They also will tend to take a permanent compression set when they're tightened up. So after a few cycles, it's very easy to start seeing leakage from a Teflon O-ring.
Yeah, Adam Trumpour has a question.
Yeah.
Hi, so back when, one second. There you go. Okay. Hi, back when you were discussing fittings, like the AN fittings and MPT fittings, what about potentially welded fittings that wouldn't be, like, the fitting itself might be like a male AN fitting that you would weld to a part instead of, threading it in? I also know that, like, in the rules there are some things about welds, but they're not specific about what kind of welds or if they're specifically for tanks or COPV. So I'm wondering, what about welded fittings that wouldn't necessarily be on a tank or COPV?
Yeah, no, you can absolutely use welded fittings, and in fact, for real high-end aerospace applications, those welded fittings are usually the preferred way to go, because even the welded AN type fittings, they're usually a lot more consistent in the kind of surface finish that you get than a flared tube end is. So by all means, if you want to go that route and if you've got the equipment to do good orbital tube welds, you're welcome to do that.
So we don't need to go to a welder with that boiler specification for these kind of welds? Like, how does that work?
Okay, you should have that type, any sort of pressure system. You want to make sure that the weld is done by somebody who knows how to weld for pressure systems.
But is there a specific certification that the rules want that welder to have, depending on the type of weld?
I think most of that is going to be an ASME certification. Mm-hmm. Mark or Scott, do you have any more feedback on that one?
No, only what you'd said, the ASME certification.
Okay. I know, a lot of any company that actually provides those types of components, even Swagelok, they can do that type of welding. So it's not a particularly exotic skill set, but you don't want to just have somebody, do it who's never welded a component like that before.
Yeah, so an example is we know of a welder who used to have I think the boiler pressure vessel certification, but that was when he was working at a company, and now he's doing his own practice, but that certification he doesn't have anymore. Like, would that still be okay because he's got lots of experience?
I would say that that's going to tie into the pressure testing section that we'll get to. If the guy has the skill set and the experience, personally, I wouldn't have any problem with that as long as you make sure to do a proper proof test of the component after it's been welded, and that's just good practice anyway.
We have some more here at Cal State Long Beach.
So I've actually gone to a welder that I work with my co-op about these to see, like, I was being silly and thinking I could go and get the welding certification. He kind of laughed at me when he mentioned that that type of welding certification takes about 3 to 4 years of schooling to get, and they have to update it every year. But he did say that if you wanted to go to any company that does pipe welding or anything like that, they will have welders available that can do part-time work, and usually those kind of guys enjoy doing part-time work on the side and will have the certification that you need.
Yeah, that's absolutely the right way to go about something like this. It's not that exotic a skill set, so you should be able to find people who know how to do that. Okay, question here about Teflon. Yep.
Is the same true for Teflon tape seals, or is that just a function of the Teflon O-rings?
Okay, so the question was, I'd mentioned that Teflon O-rings can tend to leak after a few pressure cycles. Is the same thing true of Teflon tape? No, Teflon tape is sort of a different situation, and it's used differently. So an O-ring is going to be held captive in some sort of groove or gland. Usually how prone it is to leaking is going to be a function of how effectively that gland can contain it and compress it. So the situation with Teflon tape is a bit different. It will usually last for a long time. Again, Teflon tape on pipe fittings in cryogenic applications can be challenging, but for the most part, it should last a long time if it's just a Teflon tape seal on pipe threads. So one of the things that you need to consider when you're sizing and selecting O-rings is this phenomenon called extrusion. The materials that O-rings are made of are usually available in different hardnesses, typically referred to as durometer. And there are some trade-offs with these things. So any O-ring works because it's flexible and compressible and can kind of squish into any imperfections in the metals that you're trying to seal. The softer the O-ring is, the more effectively it can do that. And so the more tolerant it's going to be to surface imperfections. The downside is the softer it is, the more prone it's going to be to failing through something called extrusion. So if you look at the figure on the left, you can see what happens as the pressure on an O-ring is increased. There's usually going to be a very small gap somewhere along the O-ring groove, and as the pressure rises, the O-ring can kind of squish itself into that space, and locally it can yield and fail. By minimizing that gap, you can cut down on the chances of that happening, or rather you can increase the pressure at which that will happen. But O-ring selection is usually going to be a trade-off between finding a material that's hard enough to limit extrusion, but also soft enough that it's going to give you a proper seal with the kind of surface finish that you're working with. They've got something called backup rings that are available specifically to prevent extrusion. And so the column on the right-hand side of that figure shows what that looks like. And basically, they tend to be Teflon rings that fill in that gap and support the O-ring material as it gets squeezed over to that side of the groove to cut down on the chances of extrusion. When you're designing your O-ring grooves, it is a little bit more involved than just cutting a groove that the O-ring is going to physically fit into. And there are various standards that you can find for how to size O-ring grooves for particular applications. But one of the things that's always important to remember with an O-ring is because they're made of rubber or plastic, it's pretty easy to nick or gouge or cut them. And so you need to be very careful that your system is designed to cut down on the chances of that happening, particularly when you're installing it. So running an O-ring over threads can sometimes damage the O-ring. The other thing that can easily damage an O-ring is if you've got one part with an O-ring in it that's being inserted into a bore. If there's a sharp edge that's going to be scraping past that O-ring, then it's going to have a high chance of damaging it. So if you look at the figure on the top, you can see that they've added a nice, generous lead-in chamfer on the mating part so that they avoid gouging the O-ring. Similarly, if you've got, say, a piston or poppet that's going to be inserted into an internal bore, like what's shown on the bottom, if that's going to be moving past a port, where that port was drilled through, you're going to tend to have a sharp edge. And so it's important to have a generous chamfer there as well, so that, again, you don't nick the O-ring as it goes past. It's also generally common practice when you're installing O-rings to lightly lubricate them. There is going to be a certain amount of friction as the O-ring is installed and as it slides past whatever component it's going to be sliding past. And so proper lubricant always helps with that. It's important not to over lubricate, and it's important to always use a compatible material. If you've got too much lubricant, that can squeeze out and that can migrate other places in your system, which you generally don't want. So now we get to valves. You will be probably using all kinds of different valves over the course of this project. There are lots and lots of types. Each of them have their particular applications. In general, all valves are going to be sensitive devices. Any valve can leak, and some are going to be more tolerant of that than others. But it's generally going to be very important to make sure that you are very careful with your valve and that you prevent any contamination from getting into it, because contaminants will very, very easily cause valves to leak. Valves are usually fairly complex components internally. It's always kind of fun taking apart and rebuilding a valve, but it can be a challenging job to do that. So you want to make sure that you know what you're doing if you're trying to take one apart and clean it or repair it. Generally, you should never operate any valve outside of its rated conditions, like we talked about. Always make sure that you've looked at the material compatibility in the broadest possible sense. Prevent contamination. And remember that valves also contain moving parts, whether it's a ball that needs to rotate or a poppet that's got to slide back and forth. And any moving part can stick. They can particularly stick if there's any moisture that gets trapped inside and freezes up. That actually happened to a rocket company in the late 80s called Amrock that was developing big hybrid rockets. And they attempted a test launch of their proof of concept vehicle, and it was a liquid oxygen oxidized hybrid. And they were testing it at Vandenberg Air Force Base, which is coastal and relatively high humidity. They had a ball valve as their main propellant valve, and what ended up happening was moisture got inside through the combustion chamber and started icing up on the face of the ball. And so when they then tried to open the valve to fire the engine, it stuck partway open. And so the rocket didn't develop enough thrust to take off, and it sat on the pad and burned. So these are some of the challenges that you run into, particularly with ball valves, because a ball has a very high surface area. And so if you get any frost on it, that can greatly increase the amount of torque that's necessary to open it or close it. So these are all some of the considerations you need to think about, and this is why it's always important to keep things very dry in any sort of cryogenic applications as well. Yeah, question?
Do most manufacturers have like assembly drawings that used to be able to know how to assemble these parts?
Right. Okay, so the question was, will manufacturers of these components typically have assembly drawings or maintenance instructions that you can use if you need to disassemble something? Often, yes. Certainly, most industrial components will. If you end up buying, old surplus hardware, then your mileage may vary. If you find yourself using really high-end components, there will be some suppliers of those types of things who keep that proprietary or don't recommend you attempting your own repairs on it. So it really varies a lot. Yeah, so if you've got a brand new valve, you might need to disassemble it. Certainly, if you have to clean it, you'll probably want to disassemble it. Or you'll want to procure a component that comes oxygen clean. That's actually fairly common, and people who make components for oxygen systems will supply them clean. So normally with something like that, you'll just get it clean and make sure that you don't contaminate it. Yeah, question in the back?
This is similar to the last question, but like in regards to
Okay, good question. So the question was, when it comes to ball valves, any preferences for 1, 2, or 3-piece valves? From my experience, I quite like 3-piece valves because it's usually much easier to take them apart. That's been my own personal experience. I find the 2-piece valves are usually a lot harder to reassemble in particular. And another question?
Yes, I had a question about clean.
Yeah.
So you said that it's possible to purchase components that are also clean, but after, let's say, a hot fire, you want to clean the components afterwards. That would still require clean.
Okay, so the question was, if you're buying a component oxygen clean, that's great, but after doing, say, a hot fire test, you might still want to take it apart to clean it. Maybe. It's going to depend on where the component is. So under normal circumstances, you shouldn't have any contamination making it back up into the oxygen side of the system. So you generally want to try to make sure that your system is cleaned and then stays clean. There will be areas of the system that might be more prone to it. So, you know, the injector area is going to be a prime candidate for fuel making its way back up after a test. So those areas you will for sure want to disassemble and clean. With other components, you may or may not need to do cleaning yourselves. If you do, obviously you're going to need to make sure that you understand how to do that, or go to somebody who does. And there are places that do cleaning and disassembly and refurbishment of components like that. Or you could learn to do it yourselves.
We have a question at Cal State Long Beach.
Yeah.
Oh, so sorry, I should have done this earlier. I had a question between the different types of fittings you were talking about. I noticed you didn't say anything about cryogenics. So is there a certain type of fitting that works better at the cryogenic temperatures, say between the flare fittings and swage fittings, or is there a different kind of fitting that's better altogether?
I think in general, all three of those types of fittings have been used under those conditions. I don't know, Mark or Scott, any particular experiences?
I actually like swage lock better for cryo than I do AN fittings. They tend to loosen up and start leaking, the AN.
Sorry. There we go.
At Purdue, we pretty well exclusively use the 37-degree flare fittings. And in fact, we buy 99% of our fittings from Parker, which are in fact the industrial tube fittings. We use some Allen Aircraft, and Allen Aircraft directly cross-references to Parker. So I don't even know where we would buy the true AN spec 37-degree flare fittings.
Yeah, I know Allen Aircraft does make them, and I think even their industrial grade ones, most of them, they make the threads to the class 3 standard, which is the major difference between them and JIC. But I think just in general with the industrial fittings, you find a lot more variation in the quality. So, you know, you can go to hardware stores and pick up JIC fittings for typical hydraulic use, but they're probably not going to be the same quality that you would get from someone like Parker or someone like Allen Aircraft fittings. So I think that's probably the biggest difference. There's a lot more variability in the industrial fittings, whereas the AN is a much stricter standard.
Right. So if you look at random different 37-degree flare fitting companies, they'll all have different pressure ratings. So that's why we stick exclusively with Parker, so we know exactly what the pressure ratings are for the fittings. But yeah, we've had a lot of trouble with swage lock fittings, and with all part-time student technicians here and the possibility of tubes that aren't swaged exactly correctly coming apart mechanically is why we don't use compression fittings for anything other than instrumentation.
All right. So moving on, we'll look at a couple specific types of valves and some of the unique characteristics of each one of them. So we've talked a lot about ball valves. They are very, very common. One of the nice things about a ball valve is that they're very low pressure drop. You've got this ball with a nice smooth port down the center, so it tends to give almost unobstructed flow, and there usually aren't any significant steps going through the valve. So they're great that way. Typically, they'll be quarter turn valves. They're available either manually actuated or using any one of a number of different types of actuators. The biggest drawback with a ball valve is the high torque that's required to open or close them. It's also possible, incidentally, to get three-way valves where you've got a common port typically coming off the bottom, and then by turning the valve 180 degrees, you can connect that through to either of the two end ports. For any low temperature use, like we talked about, it's really important to make sure you don't get any moisture in the valve because the high surface area of the ball can easily ice up. There are a couple other particular considerations as well if you're trying to use a ball valve for cryogenic services. So it's really important not to just take an industrial grade ball valve and try to use it in cryogenic applications if it wasn't designed for it. Partly this is because we talked about the danger of having any volumes inside a system where a cryogen could get trapped and then boil off and overpressure it. That can happen inside the ball of a ball valve as well. So if you can imagine, you've got your cryogenic liquid flowing through the valve, then you close it. As the ball is rotated, you're going to likely end up with some liquid trapped inside that space there. As the valve warms up and that liquid boils, if it doesn't have a way to get out, it's going to potentially blow up the valve. So on cryogenic ball valves, you'll typically see a little vent hole that's drilled through the ball so that when the valve is closed, that hole is on the upstream side. And that allows that boil off to safely vent out of the valve. The other thing that's usually important in any valve, because you've got a stem that passes through the valve that is used to rotate the ball, there's got to be a seal somewhere along that stem so that you don't get leakage up and out through the handle. Those stem seals are tricky and usually don't like to get very cold because they will tend to shrink and can leak as a result. So a lot of cryogenic ball valves you'll see, like the one shown, will have an elongated stem to get those stem seals out and away from the really cold parts of the valve. When you're using that type of valve, it's also really important to make sure that you install it vertically or nearly vertically, because if you had it on its side or even upside down, then you could get your cryogen leaking up or down into that stem and making its way all the way to the stem seal, which will again cause it to shrink and leak. So then there are solenoid valves. Solenoid valves are really handy because they're simple to automate. They use a simple electrical coil, typically 12 or 24 volts DC are some of the most common. And so it's very easy to open or close them. There are lots and lots of different design approaches to solenoid valves. Typically, they will be either two-way, on-off valves. They also have three-way or four-way valves. So those are typically used for controlling other things. If you've got a pneumatic or a hydraulic cylinder, you'll typically use a three-way or a four-way valve to activate those. These valves will typically come in either normally open, normally closed configurations. They're also available in latching or non-latching. So a typical solenoid valve has an electrical coil in it, and when you apply power, it pushes on a piston that either opens or closes the valve. The disadvantage when you're doing that is it's going to be consuming power for as long as the valve is in its actuated position. Some solenoid valves actually have a limited duty cycle, so it's important to look at that if you're buying one. It might not be possible to operate it for more than a certain length of time before it overheats. So that's an important consideration. Sometimes you would actually rather have a valve that only consumes power when it changes state. And those exist, they're called latching valves. And so if you've got something that needs to be, turned on and left on for hours and then turned off again, you might not want it to be drawing power that entire time. You also sometimes might want something that's going to fail in the last state that it was left in. And latching valves will do that as well. But again, you've got to look at your specific requirements to see which is the most appropriate. Latching valves are much harder to find, and they're usually much more expensive, so they're not nearly as common. Any solenoid valve tends to be a particularly sensitive device. They also tend to be relatively small. So you don't typically find really large solenoid valves that would be useful as, say, a main propellant valve, because the solenoid doesn't scale well. Big solenoids get very, very heavy. So typically, they'll be used for either handling lower flows, things like purges maybe, or to provide pneumatic or hydraulic power to actuate something bigger. Then there are check valves. Check valves get used quite a bit in rocket applications. They are simple devices on the face of it. They work by differential pressure and effectively allow flow in only one direction. There are lots of different styles of them. One of the more common ones has a sliding poppet inside the valve with typically a fairly lightweight spring that's going to keep it in a closed position when there's pressure coming in one way. If there's pressure on the other port, then the spring force gets overcome and the poppet slides and opens the valve. They're useful devices, but they do tend to be very failure prone. They are quite sensitive to contamination. And so if you've got any applications where, say, you've got a pressurant tank that's pressurizing both your fuel and your oxidizer, you never want to rely on a single check valve as the only thing that's preventing backflow from one tank to the other. Generally, people run into nasty explosions when that happens. So it's very, very important to pay attention to that type of situation. Another important sizing criterion for check valves is something called chatter. You might think on the face of it that if anything, it's great to err on the side of making your valve bigger than it needs to be, but that's not always the case, because if the flow through the valve is very low, then you can actually have the valve opening and closing very, very rapidly. And so you'll hear kind of this high-pitched humming sound when it does that. That's called chatter, and that can prematurely wear out the seals on a valve. So undersizing a valve is not great, but neither is oversizing it sometimes, particularly when you're dealing with a check valve. So then we've got relief valves. We talked about pressure relief valves quite a bit and how they're typically used. There are lots of different types of relief valves. The most common ones will have a fairly heavy spring that acts on your valve poppet or whatever the valving element is. And when the pressure at the inlet to the relief valve overcomes that spring force, the valve opens and relieves. Many of them will come with an adjustable spring, so you can set it within certain tolerances. Relief valves usually are not particularly high precision devices. You can get them typically within a few percent. Normally, you'll size them to make sure that your pressure in the system doesn't rise more than about 10% above the maximum working pressure. And like we talked about earlier on, it's really important to size them for the maximum flow that they're going to need to be able to handle. And so a really common way to do that, if you're dealing with something like a propellant tank, is to assume that a pressure regulator upstream has failed full open. So you look at what the flow rate from that regulator could be, and you make sure that your relief valve can swallow that. And typically, manufacturers of those valves will provide flow curves that help you to size them properly. Another thing that's important to note with relief valves is you might set the pressure to something specific, say 500 psi, but you can't operate it right up to 500 psi. It's not a step function the way they open. So as the pressure gets closer to the set point, the valve will tend to start to leak a little bit. And as the pressure rises a little bit more, it'll leak more to the point where you'll typically hear a very faint hiss. That's usually referred to as the cracking pressure. And then as the pressure continues to rise beyond that, you'll reach a point where the valve just opens more and more to the point where it's full open. So it's not just a simple binary on-off valve. It's going to be a range that you'll need to account for in how you size it. Then there are rupture discs. So this is the other really common overpressure protection that you'll probably run into. These are commonly used as a last resort. Relief valves are nice because they're reusable, whereas a rupture disc incorporates a very carefully manufactured metal diaphragm that's designed to fail at a very specific and usually relatively low pressure range. It's important to note that any rupture disc, again, won't be perfectly precise. There will be a particular tolerance band that they'll prescribe with it, and so you need to size it based on the highest pressure that a disc at the maximum end of its tolerance region might allow. The other thing that's really important with a rupture disc to remember is that it's going to be rated to a particular pressure at a particular temperature. If it's being operated at a different temperature, then you've got to try to figure out what the actual burst pressure would be at that different temperature. So most materials tend to get stronger as they get colder. Stainless steel will tend to do that. So if you've got a rupture disc that's rated to a given pressure at room temperature and it chills down to minus a couple hundred degrees, the burst pressure is going to tend to go up. So that's going to be something that you're going to have to account for if you're using a rupture disc. If you want redundancy in a system, it's pretty common to use a pressure relief valve as your primary overpressure protection, and then a rupture disc set to slightly higher pressure as the last resort if either the relief valve sticks or if the relief valve isn't able to handle the complete flow on its own. When you're using one of these rupture discs, it is important to think about where you're installing it and where the fragments are going to go if the disc bursts, because typically there will be debris that comes with a blown rupture disc. So you want to make sure that no one is going to be hurt by it, or it's not going to go firing into something that's important. The other thing that's important to remember with a rupture disc is if you've got one that's sized for a particular pressure, you can't operate right up to that pressure safely. Usually the manufacturer will tell you what percentage of the rated pressure you can go to. And if you start going above that, then you'll typically start yielding the disc. And that number is usually about 70 to 80% of the tag pressure on the disc. And so whatever manufacturer you're looking at for such a thing will tell you what that is. But it's important not to exceed that pressure, or else you'll start compromising the disc. Okay, then there are pressure regulators. These are probably among the most complex components you're going to run into in a fluid system. There are lots and lots of different styles and lots of different designs. The most common ones you'll probably run into are hand-loaded regulators like the one on the top. So the typical regulators that you'll use on industrial gas cylinders, whether it's for welding or filling helium balloons, will be that type. Those typically have a fairly small orifice inside and either a diaphragm or a piston and a spring that bears against that diaphragm or piston. And so as you rotate the knob, it's going to compress that spring, and the regulator will derive its set point from that. So any regulator has a number of just basic elements that they'll all have in common. One of those is this internal valve. And fundamentally, what a regulator is a variable valve. There'll be some sort of means of adjusting that set point, like that knob compressing a spring. And there will be some mechanism for sensing the difference between that set point and the actual downstream pressure. And then it'll translate that into physical motion of the internal valve. Generally, hand-operated regulators have a fairly small valving element inside, and that is going to effectively limit the flow. So just like with any other components, you need to size a regulator for the flow that it's got to be able to handle, and there will be flow curves that you can get to help you do that. If you need higher flows than what you'll get with a typical hand-operated regulator, they also have a type referred to as a dome-loaded regulator. So the picture on the bottom right shows one of those. And in place of using a knob and a spring, they'll typically have a cavity that you can pressurize remotely. And the pressure in that cavity will set the regulator's set point. One of the nice things about that type of regulator is they tend to be a lot more stable and will hold the pressure a lot more constant than you'll tend to get with a spring, because any mechanical device is going to have a certain amount of internal friction and a certain amount of losses as a result. So dome-loaded regulators are much more stable, and they're much more readily available for high flows. But with any pressure regulator, you've got to remember that they don't actually work nearly as nicely as you would expect them to. So ideally, what you would want with a pressure regulator is something where you can set the pressure, and then regardless what the flow through it is, it'll hold that constant. Real regulators, unfortunately, don't do that. And there are a few nonlinearities that are common to pretty much any regulator. One of them is that the outlet pressure will tend to drop as the flow increases. So if you are pressurizing, say, a tank, and you've got no flow out of the tank, so you set your regulator to get your tank pressure to where you want it, and then you open a valve downstream, you're going to find that the regulated pressure is going to drop. And depending on the particular type of regulator and how it was sized, it could actually drop a lot. Similarly, if you've got a regulator that's flowing and then you shut a valve to stop that flow, the pressure is going to tend to rise. Not only will it rise back to what it was at the zero flow condition, it'll actually tend to rise a little bit above that. That extra pressure rise that it experiences is commonly referred to as lockup. So it's important to remember that you could actually see the pressure creeping above the set point just under normal operation. The other thing that you run into with regulators is ideally, your source of pressure at the inlet to the regulator would be more or less infinite. And regulators are great if you have an infinite reservoir feeding them. But in something like a rocket, you're probably going to have a pressurant tank that starts off at fairly high pressure, and by the end of the burn is now very nearly empty. And when your inlet pressure varies over a wide range, that will usually also cause the set point of your regulator to drift. Again, some designs are more prone to that than others, but it's something that's important to bear in mind. There are two-stage regulators that you can get that will tend to or try to compensate for some of that, where the first stage regulator gives a more fixed pressure to the second stage, and then it regulates it the rest of the way down. there are other things that you can get using more elaborate, electromechanical pressure regulators, even that will actually actively sense the downstream pressure and adjust themselves automatically. Those are obviously higher cost and more complex, and not appropriate for every application. But these are some of the things that you've got to be aware of if you're trying to find a regulator. And in any case, just like any other valve, pressure regulators can leak. And so at its worst, a regulator can act like a simple orifice. So you want to figure out what the maximum size of that fully open regulator orifice is going to be, and then make sure that you size everything downstream so that it can handle that flow and vent it safely if you run into that. Now, if you're dealing with cryogenic fluids, you've got a whole bunch of additional considerations that come into play. And we've looked at a few of those things. We talked about boiling, so you've got to avoid any trapped volume that could boil off and have nowhere to go. Insulation is another consideration that you're going to run into for any cryogenic fluids. And there are two aspects to that. One is purely practical, that if your system is uninsulated, your cryogen won't stick around for very long, which might or might not be a problem. But on a safety standpoint, the other concern is that the metal of a cryogenic system, if it's uninsulated, is going to be really cold. And so it's very easy for somebody to burn themselves if they touch it. So sometimes insulation is going to be a good idea if for no other reason than cutting down on the chances of anybody physically hurting themselves if they bump into a cylinder like that. But if you're using insulation, again, you've got to think about material compatibility. A lot of insulation materials are flammable, and so you need to look at what the chances are of a leak, allowing, say, liquid oxygen to drip onto your insulation. There are design approaches for trying to deal with that, but it's something that you've got to think about. Valves, as we mentioned, there are a whole host of unique considerations that you run into if you're trying to use your valve for cryogenic operation. Any valve is going to involve a certain amount of surface area that can transfer heat in and warm up your cryogen. Valve components will obviously undergo thermal contraction at cryogenic temperatures, and if you've got dissimilar materials that are contracting at different rates, that's important to bear in mind. If you've got a valve, say something like a ball valve, where you're going to have seats that are sealing against the face of your ball, you're probably going to want it to seal at room temperature, but as the ball shrinks, you're going to need it to still seal when it's at low temperature. And so that's another of these important aspects if you're trying to find a cryogenic valve to use. Moving parts can easily ice up and stick. Stem seals can very easily leak. And there are industrial cryogenic ball valves that have been specially designed to address these. There are also aerospace grade valves that have been designed to do the same thing. You might find yourselves making your own valves, but these are all the kinds of considerations that you're going to need to address with any part that you either procure or design yourselves. Then there are the pressure vessels. So these are obviously some of the major components of any high pressure system. Just like with everything else, you've got to focus on material compatibility over the complete range of operating conditions. In many cases, 300 series stainless steels will be the go-to material for most industrial applications. They're generally compatible with a wide range of fluids, and they behave fairly well at cryogenic temperatures. If you're using hydrogen peroxide, you also need to think about passivating your tank, because a lot of things will tend to encourage peroxide to decompose. And ordinary stainless steel is usually not inert enough to prevent that. So there are treatments that you can do to build up a passivated layer on a stainless tank if it's got to be exposed to something like peroxide. Any tank is...
Adam,
Yeah.
Adam?
Yes, sir.
Hey, I'd like you to emphasize the drilled ball on cryogenic ball valves.
Mm-hmm. Yeah, yeah, that's always going to be a really, really important consideration, and it's something that a lot of people don't think of when they're looking at choosing a valve for those applications. But any small volumes like that, whether it's a ball or something else in a valve, needs to be vented just the same as everything else. Yeah, question. Correct. Yeah.
Does the same problem exist if it's an homogeneous pressurized experimental system, which is not technically a cryogen, but I can see still capturing that issue with the normal ball valve and closed off a normal ball valve with nitrous cement. It would just hold that in that ball.
Okay, so the question was, do those considerations about a vented ball apply to something, to say a self-pressurizing fluid like nitrous oxide? Not to the same extent. You're obviously not going to have to worry about the nitrous, warming up to the point of overpressurizing the ball. So that's not the failure you need to worry about. You might want to consider the possibility of having this very high pressure trapped fluid in your ball. That could easily leak out if you suddenly open it. Yep. Generally, I haven't found people being all that concerned about drilling balls for nitrous valves, so it's not as important, but it might not be a bad idea if you're concerned about any sort of trap propellant there. Yeah.
Drilled ball valves are absolutely required for hydrogen peroxide use.
Is that again the danger of a little bit dribbling out after the fact?
No. Hydrogen peroxide is always slowly decomposing, and if you have a ball valve that does not have a drilled ball, the valve will explosively disassemble itself.
All right, there you go. Another question in the back. Normally that's going to be drilled from the upstream side, and the reason for that is when you've got a ball valve with pressure, higher pressure upstream than downstream, it's going to tend to push the ball away from the upstream seat and into the downstream seat. So it's relatively easy to get a small amount of leakage from the upstream side into the ball, but that added force pressing it against the downstream seal is going to tend to prevent leakage that way. So what that means is if you had the hole drilled on the downstream side, then what could happen is as it pushes away from the upstream seat and into the downstream seat, you could still end up with a bit of leakage into the ball, but now it can leak straight through that hole you've drilled and carry on right downstream into the rest of the system. So that's typically why they put those on the upstream side. Yeah, that's a really good point. All right, any other valve questions before we move on? All right, so back to tanks and pressure vessels. Overpressure protection is always going to be very important. It needs to be sized for the worst case scenario, like a failed open pressure regulator. But we're going to draw a distinction between tanks for ground support equipment and tanks for flight. So we talked about the ASME boiler and pressure vessel code. Generally, ground support or test stand tanks should be designed to the ASME code for safety reasons. For any sort of test stand, what you really want is a tank with an enormous safety factor. because it's going to be used in the most unpredictable period of testing your propulsion systems. So it could have to withstand a lot. And usually it's also going to be close to a lot of equipment that you probably don't want to damage. Unfortunately, with flight weight tanks, usually it is not possible to have such high safety factors because then your rocket would be too heavy to fly. And so you can go lower than that. Definitely under no circumstances should you be going below a safety factor of 1.5 for a flight weight tank. And the systems requirements document for the Base 11 challenge gets into the recommended safety factors and some of the additional testing you've got to do if you try to go with factors on the lower end. But when you're using low safety factors on flight weight tanks, you should never ever be near those tanks when they're pressurized. You're not going to know how close they are to failing. And so it's just as good safety practice recommended to just assume that it could blow up at any time. As a result of that, it's going to mean that you're also going to need to make sure that your system can be pressurized and depressurized remotely, and that you've done something to think about the possible failure modes of that system so that you don't run into any situations where you've got a rocket that's under pressure and you've lost the ability to depressurize it. So things like vent valves that are designed to fail open can be one piece of trying to address that. Now, composite pressure vessels are a whole other beast. There's obviously a real attraction to using composite materials because they can be very, very lightweight, but they come with their own set of challenges. Composites will fail in ways that metallic pressure vessels will not. One of the most common things that you run into with a composite vessel is what's called a stress rupture failure. So unlike a metal pressure vessel, where as long as it's continuing to pass its recertification pressure tests, it's sort of good to use more or less indefinitely unless something actively compromises it. Composite pressure vessels can work fine until they suddenly don't anymore and fail. The other challenge with any composite pressure vessel is that there is an awful lot of stored energy in the composite overwrap. Effectively, you've wrapped your vessel in slightly stretchy filaments, and so as it stretches when it's under pressure, it stores energy. And so when a composite vessel lets go and that releases, it's usually pretty spectacular. Composite tanks are usually available either in what are called COPVs, composite overwrapped pressure vessels, which use a typically metallic liner, and then the composite overwrap goes on the outside to reinforce it. Those can be nice because the liner provides an impermeable barrier and usually is also more compatible with a wider range of fluids than just a straight composite would be. You can also get linerless tanks, and linerless tanks are in a way the holy grail because you save the weight of that metallic liner and the complexity of trying to design it in. But this produces a whole host of challenges. Whenever you're dealing with a composite for cryogenic service, you're going to run into the fact that your fiber, your resin, and potentially your liner are all going to have different coefficients of thermal expansion. And so as you chill them down, you can very easily find cracking starting to happen, or you can get your liner pulling away from your overwrap. A lot of composite materials will actually have a negative coefficient of thermal expansion so that as they chill down, they actually expand. So if you've got a metallic liner on the inside, those two things can be working against each other. The other thing that you run into is that most composite materials are quite combustible. Usually they are less combustible when they're properly cured, but if there's any uncured resin, then that tends to be majorly combustible. So for all of these reasons, composite pressure vessels in general, but composite liquid oxygen or oxidizer pressure vessels in particular are a really serious challenge. It's not an insurmountable challenge, and we've started to see launch vehicles like Rocket Lab's Electron that are actually using all composite tanks. But it's something that requires an awful lot of care and careful engineering and careful testing. So on the subject of that testing, there are going to be a number of different tests that you're undoubtedly going to need to do with any system that you're developing. One of the most basic is proof testing. And particularly for any components that you've fabricated yourselves or specifically modified, it's really important to put it through a proof test. So in any of these tests, what you're basically trying to do is pressurize it to a stress level that's going to be higher than what it would be experiencing under normal operating conditions, but not so high that you damage or compromise the vessel. Any of these tests should always be done with water or an incompressible fluid, never with gas. As we talked about earlier on, there's a lot more energy stored in a compressible fluid than in an incompressible one. And so if you have a vessel burst with pressurized water inside, you're going to have a good splash. If it bursts with compressed gas inside, you're going to have a large bomb. For that same reason, you need to make sure that when you're filling your tank with water before doing one of these tests, you make sure that all the air is bled out, because again, you want to minimize any of that high energy compressed gas inside your tank. And whenever you're doing one of these tests, the reason why you're doing it is because there is a chance that your pressure vessel should fail. So govern yourselves accordingly and make sure that people are going to be at a safe distance when that happens. It's also important usually to do this testing before you do any final cleaning on the tank, because potentially you could end up introducing contamination with whatever fluid you're using to do your test with. Yeah, question? How do you go about cleaning the inside of a tank? There are probably a whole host of different answers to that. With any sort of cleaning, I mean, one of the basic questions is, what's the contamination that I'm trying to deal with? And so the answer is going to be different for different types of contamination. I've done everything from using pressure washers to partially filling it with a cleaning solution and putting in some stainless steel nuts or things like that I can then sloosh around, and it'll help abrade the surface of the tank a little bit and kind of scrub anything that might be inside it. Tanks can be challenging to get clean. Generally, it's a good idea to try to make sure that your openings on the tank are going to be large enough that you've got some hope of being able to not just get inside to clean it, but also to inspect it. So being able to stick in a borescope or something like that so that you can actually examine it after you've cleaned it to make sure that there's no obvious contamination left is also going to be particularly important. Does anybody else have any particular thoughts on things that work well for cleaning tanks? No? Okay. Yeah, another question.
How do you inspect to ensure that you've gotten all the tanks smaller than
Okay, how do you inspect it to make sure you've gotten all the contaminants out? The oxygen system safety training materials actually will get into some of the techniques that can be used to inspect things. Generally, visual inspection will go a certain distance. Black light inspection is pretty common as well. Generally, you know, if you've got something like a bore scope that you can insert into the opening of a tank. Yep. B-O-R-E, scope. Yeah, they're basically cameras with either a thin, rigid, or flexible neck that you can just insert inside something and then kind of move it around to inspect. That's really common on high-end aerospace systems. For amateur work, I don't know how many people tend to do that. I do that, but I'm usually someone who errs on the side of being extra cautious.
Well, I was just going to say, I think it would probably be a bad idea to take a tank and turn it into an oxygen tank. I don't think you're going to. I think it would be ill-advised to find a tank that you think is made of the correct materials and decide to turn it, that you can clean it and turn it into an oxygen tank. It needs to have been an oxygen tank and been in service as an oxygen tank from day one. If you are manufacturing a tank, like a flight tank that you intend to use for oxygen service, it would be a great idea to clean the components prior to welding, such that you kind of have a known entity all the way through the fabrication process, so that you're not trying to remove some mysterious material or things like that as you go.
Yeah. But then re-clean it after you weld it.
Oh yeah, you definitely want to clean it again after welding. But a lot of times you may want to put a diffuser and or a vortex brake in your tank, and depending on the size of your tank, you may not really be able to access the inside with an endoscope or a borescope.
Oh, also there are commercially available endoscopes for about $25 on Amazon that we've used successfully in the past for multiple operations. So cheaper alternative to a borescope, not as necessarily high quality, but totally available.
Yep. Yep. Yeah, they're fairly easy to find, and usually the quality is perfectly good if you just want to do some sort of very quick inspection to see if you've developed any contamination from, you know, for whatever reason. So the other type of testing that you might want to do on a tank that you've developed yourselves is going to be burst testing. It's one thing to design a tank for a particular burst pressure, but it's very, very common to have pressure vessels fail, especially at the welds, at a small fraction of the pressure it was designed for. So if you're trying out a brand new design, it's a really good idea to try burst testing on it, which looks an awful lot like proof testing, except you take the pressure higher to the point where the tank fails, and you see where that actually is. It's also doubly useful because once you've burst a tank, you can actually see what point it's failing at. You know, most commonly, that will tend to be at things like boss welds, which usually are pretty significant stress risers. But having that experience is always useful to get a sense of whether your design and your manufacturing processes are actually producing the tank that you think you're producing. Especially if you're designing tanks with lower safety factors. So one of the things that we require for the Base 11 challenge is that any pressure vessel with a safety factor of lower than 2 needs to have at least one identical article put through a burst test, so that you can try to substantiate that you're actually getting the safety factor that you intend. And as we mentioned, composite tanks are especially violent when they let go. So you need to be very careful with doing that type of testing. Something else that you might want to do, especially for something like a liquid oxygen tank, will be cold shock testing. So this is very common for cryogenic systems, where you will assemble your system and then do an initial chill down with usually liquid nitrogen. Always making sure that the liquid nitrogen you're testing with is properly clean so that you're not introducing any contaminants to your system. Once you've chilled it, You can then drain it, allow the system to warm up, retorque any fittings, and then inspect for any obvious signs of cracking or distortion or other potential damage. So this is usually recommended for any sort of cryogenic systems. And typically your biggest candidates for failures are going to be welds or other joints. So those tend to be the areas that you want to pay attention to. And this is a good idea just to make sure before you actually get anything to high pressures that you've made sure that at least you're not experiencing any problems due to the thermals. The other type of testing that's going to be done all the time will be leak testing. And this is something that you're going to do not just for the overall system, but probably for individual components that have their own internal leak paths, things like valves and pressure regulators. So normally you'll do this kind of testing. I guess the short answer is anytime it's needed. So whenever you have done something to change your system, whether that's disassembling something, adding a new piece to it, swapping out a component, it's a good idea to do a leak test to make sure that you haven't introduced any new leakage. Even if you're transporting something to a test site where it's going to be bouncing down a gravel road, you might want to do a thorough leak test on it before you progress with any further testing, just to make sure that nothing came loose along the way. Whenever you're doing any of these leak tests, you want to make sure that it's done at a lower enough pressure to be safe, because typically you'll use something like helium for this type of testing. Helium is especially good because it's really good at finding its way out of things. And so as a leak test fluid, it's ideal. Plus it is inert, and as long as you're using clean and ideally filtered gaseous helium, you're not likely to contaminate your system with it. When you're doing these tests, because you're using a compressed gas, obviously that stored energy poses a new hazard. So normally this kind of test is going to be done at significantly lower pressures than operating. So typically less than 100 psi, and definitely never more than about a quarter of the operating pressure. And then once you've got your system pressurized, you can use soap solution or the Snoop fluid that was talked about earlier on. You can also get helium leak detectors that will come with a little probe that you can hold next to a joint, and they're useful for sniffing for leaks. I've had really good experience using that type, and I find them to be a lot less messy than soap solutions, but either approach works quite well. And then once you've tested your system and discovered any leaks that you might encounter, it's always important to depressurize it before you go and start trying to retorque anything. So now on to the operations of these systems. Yeah, question in the back. Depends on what the test is. So the question was, when you're doing these types of tests on tanks, should they be done with just the outer shell of the tank, or should it be done with any sort of internal components? It's generally you're going to want to do this as like a final step once you've got your tank all assembled. So if there are going to be baffles in it, by all means use the baffles. Usually baffles in tanks get built into the tank, so I'm not sure how you'd really be able to do that without them there. Yeah, the important thing is it's got to be the actual final assembled system so that it's truly representative. Okay, now when you're operating these systems, having carefully designed and tested them, there are a few things you need to bear in mind as well. The most basic is to be cautious. We looked at what can happen when you've got a failure of these types of systems, so be aware of how these things can go wrong and use a certain amount of common sense. The buddy system we talked about early on, that's always recommended for these operations. and the team members who are actually performing any operation should know what they're doing. If you don't feel comfortable doing something, then don't do it. Step back, learn, ask people, seek out whatever training you need, and then only go forward once you've been suitably trained and feel confident in what you're trying to do. So you need to understand not just the operation itself and how that's supposed to work, but you should also understand the fluids that are going to be involved, the personal protective equipment that's going to be required, and any other hazards that might be present. So this is all part of the basic training that you need before you go and operate a system like this. Yeah, question. Is there such thing as too much PPE? Okay, so if you don't know what PPE you need and you just put on absolutely everything, is that a problem? Well, the problem is if you don't know what you need. You should always make sure that you understand what the hazards are and what the necessary PPE is, and not just grab it whatever happens to be close by. So when it's something like a gas mask, there are different types of filters for different types of things you might be exposed to, and so you've got to understand just specifically what the hazards are so that you make sure you're using the right thing, because there's no point in wearing PPE that isn't going to actually help address the problem. Now, I suppose there's nothing wrong with using like a full scape suit for absolutely everything if you've got hundreds of thousands of dollars to spend on those things, but it's going to be much better for everyone, I think, to just make sure that you're familiar with what the recommended PPE is for something, and just make sure that you've got it on hand before you try to do anything with it. And usually the kinds of things that you're going to be using here don't require anything terribly exotic. It's all pretty basic stuff, so there's really no excuse for not making sure that you've got the appropriate equipment on hand.
I had a quick question about the leak checks. So like when you're leak checking and your pressure source is regulated down, do you typically take any extra precautions for the case of that regulator failing open and being greater than 25% of your normal operating pressure?
I'll say that what I normally do when I'm doing a leak check like that is, first of all, to use a small low volume regulator, and I'll have a valve between the regulator and the system so that once I've got it up to pressure, I just shut that valve. So you certainly want to make sure that you consider those failure cases just like you would with everything else. But with a leak check like that, it's usually pretty easy to just use equipment that has high safety factors, and make sure that you've got valves in place so that you can shut things off easily enough. All right. So another thing that's going to be important to consider with any operations of these types of systems is the possibility of failures and what happens if a failure does happen. And so systems that have been designed in accordance with industrial practices, if you're using off-the-shelf high-pressure regulators and plumbing, that's not typically considered very dangerous. Whenever you're using your own components or anything that you've designed, particularly ones with lower safety factors or flight weight systems, then you need to be very cautious about what could happen if things fail, because that is a possibility. And for any of these operations, if they're using either an unproven system or one that isn't built and tested to industrial standards, then you've got to assume that they're going to fail. And if they fail, that failure is usually going to involve both shock waves because of the overpressure, but potentially also shrapnel. And so generally your choices to protect yourself from those things will be some combination of distance and physical barricades. Now, when you're using physical barricades, you need to make sure that you've actually designed that barricade properly, just like with anything else, there are going to be requirements that drive this design and specific failures that that barricade is meant to prevent against. And if you've got a barricade that hasn't been designed right, it could actually end up being counterproductive and only contribute to additional shrapnel. So having an inadequate barricade is not helpful. There are various standards. We talked about TNT equivalents, and this is a fairly straightforward calculation to do to figure out the amount of TNT that the energy in your system represents, and then there are standard safe distances provided based on those TNT equivalencies. So if you're trying to stay away with distance, that's typically how that's going to be done. Barricading is a challenging subject because how to size a barricade is going to depend on exactly how your tank fails. So if a tank bursts into 2 large pieces, that's a very different situation than if it shatters into 100 tiny fragments. Normally, the way that people will do this on proper industrial facilities is to just use really thick concrete barricades if people need to be nearby. With something that's got to be portable, obviously that's a little bit more problematic. So probably you're going to want to err on the side of safe distances. But in any case, it's always good practice to try to look at the TNT equivalents for your system to get a sense of what that actually looks like, and then figure out your safe distances accordingly. All right, that concludes the high pressure system safety course. Thanks for sticking with me on this segment, guys. And any final questions before we move on? Yeah, Oleg.
So for the barricades, for the blast-proof barricades, the shrapnel-proof, would something on the like a really thick polycarbonate sheet or something like that still be considered a good option?
Okay, so the question is, for a barricade, would really thick polycarbonate sheets be a good option? The short answer is it depends. It's going to depend on, well, how thick and also how it's restrained. The barricade needs to physically stay in place against whatever is impacting it. People certainly have used thick polycarbonate for barricading in certain circumstances, but you're going to need to design for it.
Question over at CSU.
Yeah.
Yeah, are there any known standards for, say, TNT equivalents to barricade design or kind of construction, say, in a large field where you can actually move dirt around or something like that?
Not as much as you might like. I think the reality is that portable barricades are not typically common. Usually people will say use a really thick concrete wall or a dirt embankment or thick steel plates and kind of be done with it. There have been a number of fairly good studies done looking at different approaches to barricading. So there's some stuff out there, but you've got to remember that the error bars on those analyses are going to be pretty large. So when in doubt, err on the side of overbuilding your barricade. Even things like sandbag walls are usually pretty good. But it's good to not just rely exclusively on that, and also make sure that you're a safe distance away.
We have another question here at CSU. What methods have you devised for insulating pressure transducers against cryogenic fluids? And is there a way to do that for using a pressure transducer that isn't specifically designed for cryogenics? Because the ones that are specifically for that are incredibly expensive.
Right. So if you want to avoid the incredibly expensive ones, obviously you're going to need to look at the material compatibility, because not all pressure transducers are compatible with, say, oxygen, whether liquid or not. But for the cryogenic piece of it, usually the easiest way of dealing with it is having a fairly long length of stainless steel tubing standing the transducer off from the thing that you're trying to measure.
Gotcha. Thank you.
No problem. Anyone else? All right, thanks a lot, guys.
Are we taking a break? You're muted. I can't hear you.
Yeah, we're taking a break over here.
I put